Hello and welcome to week 2 of our class. My only comment to you guys is that you should feel free to call, text, or email way more than you have in the first week. I'll be happy to accept your calls, your texts, and your messages. Let us start with the second week. The ancient Greeks and Romans already believed that the earth was round, and they had a fairly strong idea and a good idea about the distance between the earth and the moon. That's where the agreement ended. In lecture 2 you have seen why Aristarchus of Samos thought that the sun was in the middle, and how he tried to measure the size of the sun. He failed to convince. From Aristotle through Archimedes and Ptolemy, the ancient Greeks perfected the geocentric model, where the spherical Earth was in the center of the universe. I will briefly touch on this model next. I will then tell you a bit about what happened in science in the intervening 1500 years. It took those 1500 years until Copernicus' book came around. Copernicus reintroduced the heliocentric model of Aristarchus. I will tell you briefly about this dude, but most of the lecture would be dedicated to 3 observations: phases of the moon, the fact that we have seasons here on Earth, and the difference between sidereal and solar days. These would be the first 3 ways where we will talk about how we know the Earth is not in the center. Let us start with the geocentric model. Please click on the link below and watch a 2-minute video that describes the geocentric model, the model of the ancient Greeks, where the Earth was in the middle. As you will see, these guys were no dummies. However, the model is fairly intricate and fairly complicated. The link below is to a web page that I've maintained for a few years. In it you'll find a comprehensive table that deals with the history of science between ancient times and the present. Let me summarize in a few sentences. The Greco-Roman world missed some very crucial tools that would have allowed it to accept the heliocentric system if they had those tools. These tools were developed in parallel in India and later on in parts of the Muslim world. For example, the principle of parsimony is something simple that most of you are familiar with, but it wasn't familiar to the ancient Greeks. That's the idea that if there are 2 models that explain a phenomenon, the simplest of these 2 models is more likely to be correct. Guess what the source is of the word revolution, as in the American Revolution, for example? Yes, it is related to Copernicus. Copernicus studied medicine in Italy in the late 1400s. In his spare time he learned Greek books, some ancient Greek books about astronomy, and observed astronomical observations without a telescope, because there weren't any yet. He's done that with his pals back in Italy. Back in Poland, he was the king's physician, he was a monk, and he did observations of stars and planets. In 1532, on his deathbed, he published a book. The book is called On the Revolutions of the Heavenly Spheres, hence the word revolutions. A revolution, therefore, is things that revolve around the sun. That's the source of the word. Now, as you're observing the orbit of the moon around the Earth, Please take note that this orbit is slightly tilted, hence the new moon does not eclipse the Earth. When you look at a waxing crescent moon in a picture below, what is it that you will see? Since the moon itself is a sphere, you will not see half a moon or part of a circle that's cut with a straight line, but rather you will see a banana-shaped crescent. It's only when you get to the first quarter that you will see half a moon, and then you will see a banana-shaped dark part, which is called waxing gibbous. Waxing, as in you put wax in it, therefore it's bigger and bigger. Full moon is in the opposite side, then it's a waxing gibbous, waning gibbous, third quarter, and waning crescent. Waning as in getting smaller and smaller. Before we introduce the phases of the moon again, I would like to introduce the great clock called Earth. In the picture below you see the Earth as seen from above. The sunlight is coming from the left-hand side. A person on the side furthest from the sun wouldn't see the sun because Earth is on the way. Since the person is very small and would only see the sun once he goes over the hump, just at the very top, that is the place where people see that the time is 6 a.m. A person on the left under the sun experiences the time of 12 p.m. A person that sees the sun disappears on his or her western horizon experiences the hour of 6 a.m., etc. Let us begin with the seasons. Again, only notice this orbit now and go to the next slide. Here it is again, the Earth's orbit around the Sun. But notice that the stars in the background, in reality incredibly far away, are either behind the Sun or opposite the Sun. Obviously you will not see the constellation Taurus in May, but you will see it opposite the Sun in November. That is, you will see it at night in November. What is your zodiac constellation? Think about that for a while. That is, in what month were you born? Well, you can't see your zodiac constellation during your month of birth. Interesting, isn't it? In next week's lab, you will hopefully see that the constellation we see at night at this time of the year are Scorpius and Sagittarius, zodiac constellations of the months of November and December. That is, the zodiac constellations that rise and set with the Sun in November and December are actually visible at night in June and July. Now try and think about which of these four answers is the correct one. Wait before you click on the next or arrow buttons. After you come up with the answer, click and the answer will be emphasized. Here is a slightly more thorough picture of the Earth, the Sun, and the constellations. Note that the Earth's location is not perfectly lined up with the constellation of the zodiac of the month. It's just a little off. We will talk a little bit more about it next lecture. Again, try this question. See if you can get it before you actually click. We've seen that the positions of the constellations of the zodiac can be explained nicely with Earth's motion around the Sun. Now let's look a little closer at eclipses. When I introduced the phases of the Moon, I mentioned that we didn't have eclipses every month. Here's why. The orbit of the Moon is slightly tilted relative to the ecliptic, just about 5 degrees. It is only when the nodes line up with the Sun and the Moon that we get an eclipse. We get a solar or a lunar eclipse. You can click back and forth now. I chose a picture where the setting Sun and Saturn make the main line of the ecliptic. You can see here that the Moon, and Venus in this case, are slightly off from that line due to the tilt of their orbits and the fact that the picture was not taken when the Moon was at the node. Go back to the picture with the lunar orbit. That hoop on which the Moon goes is not doing a hula hoop. It remains tilted in the same general direction for almost a year. That is, the plane doesn't swivel. The plane points towards the same direction. It's not pointing towards Polaris, it's pointing towards something a little bit away from Polaris, but it is pointing towards one direction. Well, why not exactly a year? Why isn't it keeping its plane exactly for a whole year? It's doing a very slow hula hoop indeed. So why does it do a tiny little bit of a hula hoop? More on that again in a few lectures. Just another picture of the Earth and the tilted orbit of the Moon for you to see. In this picture, of course, this tilt is exaggerated. Now, talking about those nodes. When you do have the Moon, the Sun, and the Earth line up, when would you have a solar eclipse? That is, when would you have a Moon that eclipses the Earth? In which phase of the Moon would that be? That previous question was about a solar eclipse. Let's start with a lunar eclipse though. That is, we get a lunar eclipse exactly when the phase of the Moon is a full moon, because that's when Earth is in between the Sun and the Moon, and it shades the Moon. As we've seen in lecture 2, the Moon is seen to be eaten up, and then for about 4 hours it is much darker but tinted red-brown. A fellow by the name of Christopher Columbus used this knowledge of when there are lunar eclipses to get provisions from the king of Haiti on his third voyage when he ran out. After the natives no longer wanted to provide him with nourishment, he warned them that the anger of the Moon would be upon them. Oh, but wait, Columbus was before Copernicus. How come he had predicted eclipses in his calendars? Guess what? Again, the eclipses can be explained with the geocentric model as well. Here is a better explanation for the red moon during a lunar eclipse. I understand some of you have actually seen this when it happened in April of this year. One way of telling it is that a person on the moon during a lunar eclipse will see the sunset from both sides of the Earth, actually from a ring surrounding the Earth. Go ahead and try and get this one. I'm pretty sure you will get it. This question is just a little trickier than the previous one. Now, solar eclipse is when the moon hides the sun. When that happens, areas on Earth may become completely dark, as if it was night time, and they would become completely dark at noon. Okay, the longest it would happen is for a few minutes, but indeed it does happen. Now, since at that time the moon would rise at 6 a.m. and set at 6 p.m., what is the answer to the question above? As you can see, not all of the Earth is shadowed by the moon, since the moon is smaller than the Earth. Sometimes, in eclipse season, the moon is a tad further than in other times. In such times we will only have a partial eclipse, no darkness anywhere on Earth. I like this image because it shows the regions penumbra where you would be able to see the sun eaten up by the moon but not completely cover it, and the regions where it will be totally dark. Here are a couple pictures where the sun is eclipsed by the moon and the Earth gets dark. At that time, birds are usually confused and begin to nest. Sunflowers close, and Chinese astronomers may get beheaded. Really, there's a well-known story from about 1000 AD where some astronomers in the court of the king of China were executed because they did not predict the exact time of the eclipse. In ancient times, eclipses were incredibly important and were considered omen of good or bad fortune. Here you can see where the solar eclipses paths will be on Earth in the first 25 years of this century. Notice that we will have a total eclipse near Kansas City on August 21st, 2017. Mark your calendar. This is a once-in-a-lifetime event. Also notice the interval of July 2009 to July 2010 and March 2015 to March 2016. You will note that that interval is a little less than a year. Note that during a total solar eclipse it is easy to see the sun's corona. That's something that is really hard to see when we do not have an eclipse. Therefore, we learned about the sun's corona, the sun outer layers, exactly when we observe the sun during solar eclipses. So we covered the zodiac constellations that may be explained with the motion of the Earth around the sun, and eclipses that may be explained by the motion of the Earth around the sun and the moon around the Earth in its tilted orbit. But now the last phenomenon is gonna be even more persuasive. This is not just that the motion of the planets are the way they are, but rather it is about Venus and its brightness. In his dedication to the Pope, in the book, Copernicus emphasized that Venus changes in brightness were basically the main reason that he supported the heliocentric model. Let's see, first of all, what Venus would do. This is a picture of Earth as it's orbiting the Sun and Venus as it's orbiting the Sun. Now try and imagine yourself above Earth. A person on the right side of Earth will see the sun rises, but you have to go all the way to 9 a.m. in order to see Venus rises in maximum eastern elongation. You will have to go all the way to 9 p.m. until you see Venus sets at that position. This means that at that point Venus is 3 hours off from the Sun, or 45 degrees more or less off from the Sun. And since it is gonna be setting after the Sun, this is gonna be the evening star. If you look at maximum western elongation, that's when Venus will rise at 3 a.m. and set at 3 p.m. And this is when Venus is called a morning star. And so, as you can see, Venus becomes evening star, then morning star, then goes to the other side to superior conjunction, and then back. So here is the crux of the mirror. Look at what's happening if Venus is going around the Sun rather than around the Earth. If you had a telescope, you would see this exact picture. Notice what's happening starting with a tiny Venus by the other side of the Sun. It then turns into a gibbous Venus, still fairly small, then half Venus, still fairly small, then a crescent Venus that's fairly large, then a tiny, very, very little illuminated crescent Venus that's right next to us. So it's growing, getting a little dimmer, then brighter again, and then dimming. Copernicus cataloged the brightness of Venus without a telescope because he did not have one. The telescope was not yet invented. Yet, he cataloged those brightnesses of Venus, and in the introduction to his book emphasized that this was the reason that he believed that the Earth is going around the Sun and Venus is going around the Sun, rather than everything going around the Earth. More on that in the next lecture. In our previous lecture, we've just learned about Venus, the morning star, becoming Venus the evening star, and so on, that little do-si-do that Venus does to the right and left of the Sun. And that was a little bit of an evidence for the fact that it goes around the Sun rather than around the Earth. Then the second one had to do with the phases of Venus, and that is the phase being very small, is very far away, then some crescents are the brightest, and so the changes in brightness were the main reason that Copernicus decided that Venus goes around the Sun rather than the Earth. Well, if Venus goes around the Sun and its orbit is slightly tilted, then it would sometimes be in between Earth and the Sun. This is basically Venus eclipsing the Sun. But since it's so far away, it just transits across the Sun without completely blocking its light. It's blocking very little of that light. It did so in 1882. The next time it did so was in 2004, then in 2012, and the next one will be in 2017, so good luck seeing it. We've just missed it. The film of Venus transiting in front of the Sun through different filters by NASA is spectacular, so please click on the link below. Edmund Halley didn't even live to observe a transit of Venus, but his method was used to, for the first time, measure the correct distance to the Sun, unlike Aristarchus of Samos. His trick is the following. He asked the question, this path that you've just seen of Venus across the disk of the Sun, is it gonna be the same path no matter where you are on Earth? And his answer was no. If you are, for example, on the North Pole versus the South Pole, you will see, as in the image below, if you're on the North Pole, you're gonna see the path that's closer to the bottom edge of the sun disk, and on the South Pole it's a tad higher than that. These two paths are actually incredibly close together on the sun, but there is a way of figuring out the distance's length, and that is just time the transit. If the transit is a few hours in B, it would be a few minutes less in A, and that difference would tell us via geometry the actual distance to the sun. For that purpose, Captain Cook, not Captain Hook, Captain Cook, the fellow that discovered Australia and New Zealand, was sent to the southern hemisphere. He was not sent to find Australia and New Zealand. He was sent for the purpose of measuring the length of the transit of Venus and finding the distance to the sun. In order to discuss what retrograde motion is, we first need to understand direct motion. Here is a picture of the night sky. Actually, I chose stars that rise with the sun at this time of the year. These are the stars of the zodiac constellation Gemini. I've done that for a specific purpose. But of course, if you go back all the way to December, these will be stars that are in the middle of the night sky. Now imagine you're observing them at that time. You actually take a snapshot of Gemini, then take another snapshot of Gemini 23 hours and 56 minutes later. Remember, that's our sidereal day. Keep on taking a picture every 23 hours and 56 minutes, and for a moment forget about the fact that there is blue sky and shining of objects, etc. What you should imagine is what it would look like. Since you've taken the picture every 23 hours and 56 minutes, the stars will not move. However, every month or so, you will see the moon getting into the frame and moving towards your left, basically drifting towards the left or the east. So it's doing an eastwards drift. The sun will show in the picture in June and will also be drifting eastwards. That drift of stars, of whatever celestial objects relative to the stars towards the east, is called direct motion. Now let's see why we get this direct motion. As Earth is spinning on its axis in the animation below, the moon is going around the Earth and the Earth is going around the sun. Let's see what this snapshot actually means. Wait until the Earth comes to the left side of the sun. That's when you take a snapshot. Wait until it comes to the right side of the sun. That's when you take a snapshot towards your right. Let's assume for a minute the Gemini is to our right. Then you take a snapshot every time Earth spun around so that you on Earth are facing towards the right. So that movie is a snapshot every 23 hours and 56 minutes, therefore a snapshot every time you are on the right side. Therefore, as you go around, you're taking sometimes snapshots during nighttime, sometimes during the daytime. Okay, now let Earth again pass the sun from its left. Forget about the moon for a minute. as Earth passes the Sun from its left, that's like a car going in a circle, maybe in the Indy 500 or something. Okay? After all, Earth is moving at 18 miles per second. So as you are passing the middle of the track, look at the middle of the track, which is fairly near, relatively speaking, versus the very far away mountains, for example. The faraway mountains barely move relative to you, whereas the nearby object moves quite a lot. Therefore, as you take a snapshot, you are passing the Earth by, you're taking a snapshot, and the snapshot kind of shows as if the Earth falls backwards. Falling backwards means drifting to the east, just because Earth spins from the east to the west. The same holds with the Moon, only the Moon falls behind even more. Again, try and wait until the Earth is to the left of the Sun and see what happens with the Moon. Not only is the Moon very close, it also moves backwards. Therefore, the Moon drifts towards the east in direct motion even faster than the Sun does. Whereas the Moon and Sun drift eastwards in their direct motion, the planets have weird motion. The ancients were so impressed that they called them the wanderers. Actually, a wanderer is a planet in Greek. That's the meaning of the word, because they were wandering amongst the stars. Now try and follow the animation below. It shows how Mars' direct motion changes into backwards motion and then again into direct motion. Thus Mars is actually drawing a weird shape in the sky. Here are a few more pictures for retrograde motion. The first image is multiple exposures of the planet Jupiter doing its retrograde motion. The second picture is of Mars. Now notice that this picture is slightly different than the previous picture of Mars with its retrograde motion, and the precision of that observation is going to tell us a lot about the actual orbits of planets in future lectures. And the third image that will appear will be same thing as in the animation, only in one single picture of the Earth passing by Mars. As we pass it by at first, it's regular direct motion that we're seeing relative to the stars. Then it is going to be backwards motion, which we call the retrograde motion. Let me conclude here with a story about a certain retrograde motion that happened at about 2 BC, the year 2 BC. At the year 2 BC, the planet Jupiter, associated in those times with the king of the gods, did a very interesting kind of retrograde motion. This retrograde motion at the time looked like a crown. And this crown was exactly above a star called Regulus. Now Regulus is a star in the constellation of Leo the Lion, the zodiac constellation of the month of August. This little do-si-do that Jupiter did just above Regulus basically could be interpreted as the king crowning the king of the constellation of Leo the Lion. Now, Leo the Lion in the ancient world was associated with Judea, the Lion of Judea, or the Lion of the Jews. Hence, people interpreted that as maybe this has been the Star of Bethlehem, and the crowning of the King of the Jews and the Star of Bethlehem may have been very, very rare event. This event actually happens roughly every 300 years or so. Now, there is no evidence whatsoever that this is at all related to the story of Jesus of Nazareth. The next slide is the exact slide that we've used in Lecture 3. In it, I'm showing the measurement of a parallax, basically the measurement of a faraway star that is still way closer than the rest of the stars to us. We're looking at the stars in June and then in December, or in March and then in September, basically 2 astronomical units apart. As a result, it moves, but it moves basically by 1 arc second. That's 1/60th of an arc minute, or 1/60th of 1/60th of a degree, which is a tiny, tiny amount. Bessel measured it in 1838, so please note that our ultimate proof that the Earth moves around the Sun came in 1838. That is not at the time of Aristarchus in 300 BC, not at the time of Copernicus in 1532 AD, but rather 300 years later in 1838. Take the baseline A and B in the slide before the last one to be a new baseline. Not the distance between your eyes, not the distance between the 2 sides of the Earth, but rather the distance between the 2 sides of Earth's orbit around the Sun. That's gonna be our baseline for a parallax that we used in order to find the distance to the nearest suns, the nearest stars. That's quite amazing that this is possible, but you should recognize that this was not done until the 1800s. That is because that parallax angle, that motion, is so incredibly tiny. That is how we found that the distance to even the nearest stars is light years away. That is, light coming from the nearest stars take about 3.5 years to arrive from that star to Earth. When Copernicus came along, he knew that his model must be simple enough. He also knew that it still needed to explain the precise observations. Hence, his model actually assumed that the planets are on perfect crystalline spheres, as was the Earth itself, as they orbited the Sun, and he had to add on those the same as was added in the ancient times, epicycles, etc. It took extra effort to get out of this model with perfect crystalline spheres, and that is the topic of our lecture today. This slide is just the simplest model of Copernicus, and it is here in order to explain to you or remind to you the order of the planets from the Sun outwards: the Sun, Mercury, Venus, Earth, Mars, and not included in the picture are Jupiter and Saturn. Other planets were not known at the time of Copernicus or Kepler. Note that the symbols in this image are the same symbols we're using to the present day. For example, Venus and Mars may be quite familiar to you guys. Observing the orbits of Earth and Venus, for example, from above, we see two circles. On a closer inspection, we see that this model yields Venus as the evening star and the morning star. The actual brightness graph that tells us that Venus is going around the Sun and has phases is in the next slide. Please note that this morning star evening star exchange is also true for Mercury. Mercury is even closer to the Sun, of course. More on Mercury in a couple of slides.